Hi, if you're watching this video, chances are you're interested in the field of home appliance repair. Or maybe you're already a technician who wants to reach a new level. In our case, that new level is repairing electronic modules. My name is Shukrat. By profession, I'm an electronics engineer, and at the same time, I'm the owner of the Fixer Plus Service Center in Bishkek, Kyrgyzstan. Our technicians carry out between 10 and 20 on-site repairs every day. And as an active electronics technician myself, I repair hundreds of electronic modules every month. Some things we manage to restore, some electronic modules we buy for spare parts. And in this video, I'd like to share with you, let's say, my experience that I've gained over this time, and touch on the topic of training. Back in the day, when I was just starting out in appliance repair, there wasn't the kind of structured information and online courses that are so common now. At that time, they simply didn't exist, or if they did, they were insanely expensive. Because of this, I flew to Moscow, spent literally 5 days in training there, and realized one very big and important problem. Unfortunately, the teacher and the student are speaking completely different languages. In our field, in the field of repairs, not everyone comes straight from university, well versed in technical terms and so on. Or, for example, some people come into our field from vocational schools. And when the teacher tries to explain something to the student, let's say, in technical language, using terms like potential barrier, PN junction, microcontroller, microprocessor. Unfortunately, not all the guys even understand what the difference is between a microcontroller and a microprocessor. Or, for example, what does it mean, 0 and 1 in digital technology? And that's exactly the point. That's why many students don't achieve any results. And some people don't even understand why they came to these courses, even though they're paying a lot of money for them. So guys, in this video, we'll try to sort all this out. I'll explain it in simple terms. In other words, I'll try to convey all these technical terms to you in plain, everyday language, so you can really understand the essence of how an electronic module works. So that if someone brings you a board for repair, you'll know what parts it consists of, where to start your diagnostics, and accordingly, how to fix it. And for us to be able to speak the same language, we need to go over the following topics together. Let's start, perhaps, with what an electronic module is, what types there are, and some features of different electronic modules. We'll take a look, for example, at those from microwaves, and accordingly, some of their nuances. Any electronic module is the main control part of a household appliance. It is needed to control all the processes. For example, in a washing machine, it will control the entire washing process, from filling with water to measuring the temperature from the sensors. So, when you look at an electronic module, if you haven't worked with them before, it might seem a bit. It can be intimidating, because there are all sorts of components, and you don't know what they do or what their functions are. But over time, you'll start to intuitively understand what each part is responsible for, even if you don't know exactly what the module is. So, for example, on this module, what do I see with you? I see that we have a transformer, I see we have a relay, and I also see another relay. Here are these high-power relays that are installed. Accordingly, they switch large loads for us. Possibly things like heating elements, fans, blowers, and so on. This particular board is a control module from a dishwasher. Electrolux, an industrial dishwasher. Accordingly, these relays turn on large heating elements, circulation pumps, and so on. Basically, on the electronic module, on this fiberglass board, we have tracks and spots where electronic components are mounted. Naturally, each electronic component has its own designated place. We can even see, right in the center, in the most prominent spot, a chip. The largest chip, most often, is the microcontroller. The microcontroller is like the human brain. We'll go into more detail about what this is in upcoming videos. How does it work? Next, we see the power supply unit, which is this part here. The power supply unit is the part of the electronic module that provides the necessary voltages for the microcontrollers and switches. These little things here and so on. When we look at the electronic module, we can see thin traces. These little hair-like lines that go from one component to another, these are traces, just conductive traces. Basically, you can think of them as wires. If it weren't for these traces, the board would be cluttered with a huge number of wires. If a trace breaks, you can repair it with a regular piece of wire or any kind of conductor. This board is also double-layered. There are single-layer boards and there are double-layer boards. This board is double-layered. Notice that there are traces on both this side of the board and on the other side. Here they all are. And quite often, in order to connect certain traces from both sides through holes or vias are used. And for example, in indesit washing machines, it's a common issue when the vias, for instance, rot due to high currents, corrosion, impacts, vibrations, and so on. So you need to check these traces and look for the exact spot where the break occurred. That's what concerns the dishwasher board. And now I'll show you some boards. For example, with a microwave, you'll see the difference. This here is an electronic control module from a microwave. We can see right away. There's a small display. Here we have 7-segment displays. 7-segment displays are most often used specifically to show numbers. Why are they called 7-segment displays? Because there are 7 segments involved. And depending on which command the microcontroller gives, different numbers or letters will appear here. This board is single-layered. Notice, on this side we have the traces, like these, and on the other side there are no traces. See, here it's just bare fiberglass. So, what else can we see here? We can see a separate board. This is called a subboard. The power supply unit is soldered onto it separately. So, basically, it doesn't really matter whether the module is from a washing machine, a dishwasher, a dryer, or a refrigerator. The same radio components, the same parts, and the same operating principle are used everywhere. So, this was a module from a microwave. And in terms of repair, they won't differ from each other at all. Now let's take a look at a module, for example, from a deep fryer. So here we have a module that was brought to us from a restaurant. This is an industrial deep fryer. And you can see how small the circuit board is. But at the same time, it controls various components. Here we also see a display, a 7-segment indicator, some kind of microcontroller, and small control buttons. And basically, it's all the same as the previous boards. Again, it's a double-layer board. There's also a speaker there, which signals various errors, for example. And finally, let's take a look at an electronic module from a washing machine. Indesit, this is one of their modules. There are 2 generations of it, and there's also another one called Arcadia, and there's the 123 Windy as well. In fact, Indesit has one of the widest ranges of electronic modules, so these really are quite extensive. These modules were reliable, but they had a common issue, as I mentioned before, with the connectors here. So you can notice these test points and the connectors here. For example, if you're trying to find the contacts and check them with a multimeter, and if this connector doesn't have continuity, then that's where the problem is. There's a break, and it needs to be repaired. Here it's the same story. We see a large chip, that's the microcontroller, and another chip, which is the amplifier. We'll talk about that one as well. We also see a transformer here, a switching one, and here's our power supply unit and the power relays that control the load, the heating element, the pump, the motor, the reverse, and so on. So friends, that's basically everything. We'll go through all of this step by step in the following topics. Common faults in electronics. Guys, we can group all faults in electronics or electrical engineering roughly into three types: an open circuit, a short circuit, and some kind of software malfunction. Let's start with the first one. What is an open circuit? An open circuit is when electric current stops flowing in the circuit because somewhere there has been a break in the conductor, or in our case, for example, an open circuit, meaning some conductor might be damaged, cracked, or broken due to a high current. For example, or if any of the elements in the circuit fails, for instance. I think everyone has had those string lights in their childhood that were connected in series. So each bulb was connected one after another, and basically, they were wired in series. If one of the bulbs burned out, the whole string of lights would go out, because there was a break in one of the bulbs, in one of the conductors. And the entire circuit would lose power. So an open circuit is characterized by infinite resistance, meaning the resistance approaches infinity. We use R to denote resistance. Now, what can cause an open circuit? Usually, it happens due to some kind of mechanical damage, corrosion, vibration, or, for example, if the current increases and some component burns out, then the current stops flowing. So that's the first type of malfunction or failure. The second is a short circuit. I think you've often heard this phrase, like the lights shorted out in the house, or some component shorted out. A short circuit, or SC, is characterized by a sudden increase in current in the circuit. According to Ohm's law, the lower the resistance, the higher the current. So in a circuit where a short circuit has occurred, the current suddenly increases. In this simple example, I've shown a jumper that actually shorts the entire circuit to itself. So if we imagine that this line isn't here, electric current flows and the light bulb is on. But at some point, the current finds the shortest path. For example, water gets in or some conductor falls onto the contacts. There's a sudden surge in current, and often the power supply fails. So what causes a short circuit? A short circuit can happen, for instance, if a capacitor on the board dries out. It dried out, the electrolyte leaked out, and as a result, it shorted the circuit. With a short circuit, the damaged components on the board are often immediately visible. They get charred, burn out, or sometimes even explode. Take the varistor, for example. As we mentioned in our previous videos on the channel, that's exactly its function. Its job is to immediately lower its resistance and increase the current when there's a voltage spike. As the current in the circuit rises, the conductors burn out. In other words, the varistor blows, protecting and preserving the rest of the board. So that's what happens with a short circuit, and the third type of malfunction is a software failure. It often happens that if there's another power surge, some interference in the network, or, for example, you suddenly pull the plug of an appliance while it's running. Sometimes the program crashes. Some people say the firmware got wiped. Yes, that does happen. Or does it? Also, the processor mask can get wiped, and then it needs to be reprogrammed. That's a software failure. Software failures are usually fixed by advising the user to turn the device off and then on again. Basically just doing a simple reboot. In our case, we often fix software failures by reflashing the controller. So, friends, these are our typical malfunctions, and we need to be able to tell them apart. What is an open circuit, a short circuit, and a software failure?
Can you hear that? Can you hear that? Can you hear that? Can you hear that? Can you hear that?
To make understanding and repairing electronic modules easier, we need to conventionally divide the electronic module into two parts. We have the hot side and the cold side. What is the hot side? The hot side is where we have high currents and high voltage. For example, the power supply is the hot side, since 220 volts go in there. Also, the hot side is where there is some kind of powerful load, for example, the so-called. There are motors, pumps, and so on. In other words, for example, how can you tell here where the hot and cold sides are? The hot side is this part, the power supply, power relays, chokes, filters, and so on. We can also see some heat sinks here. Basically, if I were seeing this board for the first time, I would understand that the components attached to the heat sinks are the ones that consume power. That is, high current flows through them. This current heats up these parts, and so they need to be cooled somehow. That's why these heat sinks are installed here. In this case, this heat sink is installed on the motor's triac, because the motor draws quite a large current, so the triac needs to be cooled. So, what about the other part? The cold side. The cold side is the low voltage part, where the microcontroller is located. There are also memory chips and, for example, amplifiers there. So, in this way, it's always important for us to understand in which part a problem has occurred. A malfunction can occur either in the cold side or the hot side, and in practice. We almost always have problems in the hot side. That is, it's the filters, the diode bridges that burn out, some blown resistors, triacs, transistors, and so on. Now I'll show you another module, where we'll also try together to find the cold side and the hot side. This is the control module of an Atlanta washing machine. Here we can see the power supply unit. Accordingly, this is the hot side, 220 volts. It comes in through these two connectors. This is the program selector. By the way, friends, for future reference, if someone brings you an electronic module with a selector, where you choose the programs, then 220 volts is always connected directly to this selector. Now let's take a look at where the cold side is. We flip the board over and you can see the cold side. Here it is. You can even see visually that everything here is very small. SMD components, a microcontroller, various registers, small SMD transistors, triacs, and so on. And here you can clearly see that there are thick traces, which means we know that a large current flows here. This is exactly the relay for turning on the heating element, and visually you can see that a large current flows here, so this is the hot side. And also these triacs, which control the valves, the water drain, and accordingly lock the door. So this part here is the cold side, and this is the hot side. For example, if my washing machine keeps draining water even when it shouldn't, the first thing I'll check is this circuit. Specifically, the drain pump circuit, and in particular, the triac that controls the drain pump when repairing electronic modules. You'll often have to repair power supply units, which is usually what gets repaired when someone brings them to you. The control module has a fault and won't turn on, meaning there's no power at all. Basically, the appliance just won't turn on and shows absolutely no signs of life. The first thing you'll check. Naturally, you'll look at some protective elements like fuses, but most importantly, you'll check the power sources. And in this case, you need to understand the differences between linear power supplies and switching power supplies. Linear power supplies. They were used, let's say, in the past, and then after that, switching power supplies came along, which are, let's say, more modern technology. So now, after I explain this to you, I'll show you a visual example. So, what is a linear power supply? A linear power supply, it doesn't have any digital components. So, it's basically a regular transformer that's plugged into the mains, a step-down transformer. For those of you who don't know what a transformer is, it's a device that can turn 220 volts into 3, 5, 16, and so on. So it can either step down the voltage or increase it to tens of thousands of volts, and so on. In other words, here we have a simple block diagram, 220 volts. The mains voltage goes into the transformer. After the transformer, for example, the voltage is stepped down. Let's say, for example, it drops to 16 volts, like in the example with the washing machine. After that, these 16 volts go to the rectifier. A rectifier is what evens out the sine wave, evens out the alternating voltage. Alternating voltage is usually represented as a sine wave, that is, plus minus, plus minus, plus minus. It changes 50 times per second. So what does the rectifier do? It actually evens out the sine wave. After the rectifier, which is usually a diode bridge, the power goes to a smoothing filter. A smoothing filter is just a regular electrolytic capacitor, and after that, the power goes to the voltage regulator. So you had 220 volts, converted it to 16 volts, rectified it, sent it through the smoothing filter, In other words, we smoothed out all those pulses, almost to a straight line. And then this power goes into the regulators. Here are the regulators. There can be different voltages, 3.3 volts, 12 volts, 5 volts, and so on. In our case, it will be 5 and 12 volts, but we'll get to that a bit later. For now, let's talk about some more drawbacks of linear power supplies. One drawback is often their size. They're very bulky and expensive. So, for example, finding a transformer nowadays usually requires a significant financial investment. Now, let's move on to switching power supplies. Switching power supplies. They're a bit more complex to build, and people are always striving to reduce the size of any components. Here, it's the transformer that has been made smaller. If you compare a linear transformer to a switching one, you'll really notice the difference. They're just drastically different. But to compensate for the smaller size, you have to increase the frequency. And this is a very important distinction. In a linear transformer, we first step down the voltage and then rectify it, but in a switching one. First, we rectify it, then we chop it into pulses. Into a very large number of pulses, so the operating frequency of these transformers is dozens of times higher, in the kilohertz range. Whereas in a regular household network, we have 220 volts at 50 to 60 hertz. So, when we've chopped it into these pulses, into a digital signal, into a PWM signal. In our case, the inverter is a PWM controller. Next, now we can do whatever we want with these pulses. Basically, these pulses are sent to the power transformer. The power transformer is what steps down the voltage for us. The required voltage is then filtered at the output filter. We also have feedback. Basically, these are the main differences between switching and linear power supplies. The advantage of switching power supplies is that they're fast and take up very little space. And in terms of reliability, they're not really inferior to linear power supplies, generally speaking. Plus, they're cheap. PWM controllers and switching transformers are very affordable. Now I'll show you a clear difference between these power supplies. Here's a visual example of the difference between control modules with a switching power supply and with a linear power supply. I think you've already guessed that this one here is the linear power supply. So, as you can see, there's a large mains transformer. It even has the output voltage marked on it, 16 volts. So, that's the power supply. We get 220 volts coming straight to the primary winding of this transformer. 220 volts go in, get transformed, meaning they're stepped down to 16 volts. Next, we have a diode bridge. So these 16 volts are converted into pulsating DC, which then goes into a filter, and after this filter, we end up with almost pure DC voltage. After that, these 16 volts are simultaneously supplied to the 12 volt and 5 volt regulators. So here we get a stable 12 volts, and here we get a stable 5 volts. Why do we need stable voltages? We need 5 volts because our microcontroller is the cold part, so it requires a stable 5 volts. It's a low voltage section, 11 volts. We need 11 volts to switch various relays. Now, let's take a look at the control module of the Atlant social machine. So, this is also quite a decent module. It served for quite a long time, and what was the issue here? The problem was very simple, just a cold solder joint, which we fixed. Take a look at its power supply unit. It only takes up this little space. Here it is, the power supply unit. What do we see here? We can see for ourselves. The transformer is a switching type, and it's very small. Compared to a linear transformer, the size difference is at least 5 times larger in favor of the switching one. And here we can see the inverter, specifically the PWM controller, which is the one that chops up the voltage for us. This is direct current voltage, so it turns direct current voltage into pulses. I think you've often heard the term PWM controller. What is PWM? It's pulse width modulation. So it's not just a sine wave, it's a PWM signal. Later on, we'll take a look at what that actually is. So the power comes into the selector. 220 volts comes into the barrel, gets converted. Well, actually, First this voltage is rectified, then it turns into 320 volts of DC and goes to the PWM controller. From there, these pulses are chopped up by the pulse transformer, and after that, we have the output capacitors. That's basically it. As you can see, friends, it's a very simple, very straightforward power supply. And when it comes to repairs, it's really, let's say, undemanding, so fixing it is much easier and cheaper. So, friends, I hope you now understand the difference between linear power supplies and switching ones. If you see a PWM controller, then right away, 100%, you know it's a switching power supply. Let's move on to the next stage. In order to get to the next topic, which is about microcontrollers and memory chips, we first need to understand what types of signals there are, what an analog signal is, and what a digital signal is. I think each of you has heard of the binary system, which consists of ones and zeros. But let's start with the analog signal, because the digital system didn't appear right away. So what is an analog signal? An analog signal is a signal that changes continuously over time. That is, it constantly has certain values. Well, for example, let's take wind speed. Meteorologists measure wind speed, and their graph would look something like this. So, at any given moment in time, we have some different value that can change within any range. Or, for example, volume. That's also an analog signal. A change in voltage is also an analog signal. So, for example, when I turn the volume knob, the resistance changes. For instance, it could be 0 ohms, 1 ohm, 2 ohms, 3 ohms, and so on. So, when you turn the volume knob, you're changing an analog signal. What is digital? A digital signal has only two states. That's 1 and 0. How can we, for example, describe the lighting in a room? It's dark, the light is off, that's 0. If you turn the light on, that's 1. You'd agree, it's not possible for the light to be half on and half off. Figuratively, there is just 1 and 0. For a microcontroller, it's very important that the values are discrete. A microcontroller can't receive 0, 0.5, 1, and so on. That's not how digital technology works. A signal is either present or it's not. So, the graph of a digital signal looks like this. Now, in simple terms, let's talk about what a microcontroller is, as well as memory and amplifiers. Now that we've gone over the types of signals, it'll be easier for you to understand the principle of how a microcontroller works. I'll try to explain this topic to you using an example, drawing an analogy with the human body. Let's imagine I need to pick up these tweezers. The thought that came to my mind about picking up these tweezers, the tweezers themselves won't lift or even budge on their own. I need to amplify this thought and accordingly use something that can actually pick up the tweezers. In other words, my hands. In this case, the microcontroller plays the role of the brain. So here it is, the microcontroller is the central brain of any electronic module. So here, signals are generated that are necessary for operation. For any board, meaning to turn on relays, to receive or process any kind of data. For example, a person also has, roughly speaking, their own input and output ports. Let me give you a simple example. For example, a microcontroller has input and output ports. Input ports, for instance, receive information from various sensors. So, for a person, what could be an input port? It's the eyes. They see the surrounding world. It's the same thing that the microcontroller does for us. It sees what's happening in the washing machine by receiving the necessary signals from sensors. By the way, let me jump ahead a bit and explain the difference between a microcontroller and a microprocessor. You might confuse these terms. A microcontroller is already a finished component, a ready-made complex device that you can use in your project. Inside it, there's already a microprocessor, RAM, memory devices, input-output ports, various amplifiers, and so on. There are also digital to analog converters, analog to digital converters. A microprocessor, on the other hand, is a separate device that only performs mathematical operations. It doesn't have any additional devices inside. So let's get back to our analogy. Now, let's say the microcontroller needs to turn on, for example, the heating element in a washing machine. It's time to heat the water. How does it do that? On one of the ports responsible for turning on the heating element, we had a logical 0. In other words, there's no power. 0 volts. But as soon as the microcontroller, according to its firmware, according to its program, needs to turn on the heating element, a logical 1 appears at the output of this port. In this case, a logical 1 will be equal to 5 volts. So the microcontroller will read these 5 volts as a logical 1. That's why we need to amplify these 5 volts. In this case, we have amplifier stages. Amplifiers are often either transistors or transistor arrays, like ULN. In our case, because they're common on circuit boards, you'll encounter them frequently. ULN 2003, ULN 2004, and so on. So we have a logical 1, 5 volts. Next, we go into the amplifier, and these 5 volts are turned into 12. Why? The ULN chip consumes 12 volts of voltage. That's it. Now we have 12 volts. It works like a kind of switch. 5 volts go in, 12 volts come out. Everything is amplified. Now these 12 volts can already switch the relay. So the 12-volt switch has triggered the relay, and the relay itself directly switches and controls any kind of load. It doesn't matter if it's a heating element, a fan, or, for example, any device you need, or even a motor. For example, that's basically the whole working principle. The microcontroller consumes 5 volts, outputs signals, and all of this happens synchronously.